Okay, YouTube, in this video I'm going to introduce the concept of radian measurement when it comes to angles. We've discussed degree measurement, and we're often very familiar with that, but when it comes to radian measurement, the reason why they are so beneficial to us is because we often use calculations that involve the angle. And when you're using calculations that involve angles, often when you're using degrees, you get unfortunate units. Like if you were to take feet times degrees, you would get foot degrees, which are units that make no sense, really. So if we were to take feet times a number that represents an angle but had no units, then you would get a measurement that maybe comes out to be feet, which is a sensible unit that makes sense. Okay, so what we endeavor to do, and this isn't a very old type of measurement with respect to the history of math, but we tend to want to define another way to measure angles with real numbers instead of degrees, which are fictional. Okay, and the way we do this is we often refer to using what we call radians. Okay, so what I want to do is I want to consider a circle with its center at the focus, or the focus at the origin, and a radius of r. And so this could be any circle on the planet, but basically if you can imagine, oh, that's not a very good circle, you guys. If you can imagine a circle that proceeded around the outside of this and it has a radius r, and we'll even call our angle in standard position here, and here's our radius. The simple fact is, no matter what your angle is, you know, let's say I have a central angle is what we call it, and it goes out here and it intersects my circle at this point right here. Okay, we're going to say that the radius is the same. No matter where I go in the circle, no matter how big this angle, we'll call this our central angle theta, no matter how big this angle gets, this radius is going to stay the same because of the definition of a circle. It is that all points on the outside of the circle are equidistant from the center of the circle. So that being said, since the radius doesn't change, the bigger and bigger this angle gets, if I wanted to indicate how big it was getting, what I could do is I could actually provide another measurement, and that other measurement is going to be this distance right here. And we're going to call this distance a lowercase letter s, and s, if we want to kind of write down what this means, s is the arc length. The simple fact of the matter is this: the bigger and bigger this angle gets, we could also acknowledge that the bigger and bigger the arc length gets. So one thing that's not going to change is the radius length. So if we wanted to find a real number way to define, the angle here, we're going to use what we call radians. We say radian measurement. And essentially, when it comes to radian measurement, we're going to ask this question: how big is your angle? But we're going to define it as an answer that says this: your angle is so big that this sounds like a joke, doesn't it? That this radius fits into the arc length this many times. And what I want to kind of indicate here is this: if s is equal to r, if the amount of arc length right here is the same as the length from the middle of the circle out to the outside, which is what we call the radius, then we say that this angle is 1 radian. Okay, what do you say? 1 radian. That's my favorite thing. We could also call it 1 rad. And my favoriteest thing is this: we can call it 1. And you'll notice that I don't write 1 radian. I don't have to write radians. If I don't write degrees, we assume that it is in radians. But this is a unitless measurement. A measurement that indicates an angle, but also at the same time is something that I can multiply by other things having units that won't affect their units. So, that being said, we say in general, specifically, if the radius length is equal to the amount of arc length that you've intercepted with your angle being cast here, then we say that this is 1 radian. If you wanted to double this angle, 2 radians, we could say then what you would have to do is you would have to take this arc length. Let's switch over to like an orange. And this arc length right here would have to be twice as long as the radius. So there's 1 radius length. And if you were to try to fit in another radius length, you might have an angle that's over here. And we would call this 2 radians, or just 2. Okay, so now let's get to why I'm just calling this 2 and not 2 rad. Because in general, we would say that the angle is so big that the radius passes into the arc length this many times. And so essentially we're using that fact that we acknowledge that the radius never changes to say that the bigger and bigger our angle gets, the bigger and bigger the arc length gets. So in other words, the more times the radius length fits into the arc length, then the bigger this angle must be. So in general, we say that as the arc length over the radius length. Okay, and in other words, if you wanted to write a little message here, it's how many times the radius fits into the arc length. That's how big your angle is. Okay, so a few things that I want to touch on before we move into our next video, and you'll notice that I've got this all divided up into radian measurements here. It's kind of hard to read, but we have 0 degrees, 30 degrees, 45 degrees, 60, 90. We're picking on those angles because they do relate to the special right triangles. But essentially, if theta equals s over r, the first building block that I kind of want to acknowledge is this: if I had a 360 degree angle, something like this, okay? And let's say I have, a circle of a radius r, and so my angle starts in standard position right here, rotates all the way around one time and comes back to here. If I wanted to know how many radians is this angle, what I'm really going to need to do is I'm going to need to take the radius length and see how many times it fits into the arc length that I intercepted, which is all of this arc length. And the thing with all of that arc length is we actually have a perimeter formula. We call the circumference with a circle. I almost wrote P. But we say it's 2 pi r is the arc length of one full time around. Okay, so we know that this is 360 degrees. The question we're going to try to answer here is this: how far, around, or how much rotation is this in radian measurement? And so we say that since the circumference of the arc length is 2 pi r, and the radius of just length r is just r, we're going to say that s over r in this case is equal to 2 pi r over r. And what happens is these r's cancel out and we get left with 2 pi. So one of the most important things we can acknowledge is this: there are 2 pi radians in 360 degrees. These mean, you guys, they mean the same thing. So to rotate 2 pi radians is to rotate 360 degrees. And one thing I do want to say about this 2 pi here is basically this: 2 times pi. I get about 6.28, of course, but what that means is given any circle of radius r, then the radius fits into the outside, always about 6.28 times. It would take 6.28 of these radius measurement sticks to go 1, 2, 3.14, 5, 6, 4, 5, 6.28. Okay, so we get 2 pi radians is 360 degrees. If we were to divide this 2 pi in half, split it in half, then we would have pi radians, pi rad. This time I'm going to write just rad, and I'm going to say that that must be the same thing as 180 degrees. So on my unit circle, I'm calling this a unit circle, on my circle over here, essentially you notice 0 degrees is the same as 2 pi, and to rotate 180 degrees is pi. The whole key to getting this thing down is memorizing those two measurements, because what I can tell you is all of these other measurements around the outside are very hard to learn at first, but they are fractions of pi, where pi is the same thing as 180 degrees. So that is to say, when we have a 30-degree angle here, I hope you notice this, we have pi sixths, because 30 degrees is a sixth of pi, or in other words, a 30-degree angle is a sixth of, 180 degrees. So I'm going to fill in a couple other ones here. We say pi halves is 90 degrees. I should line these up a little bit better. Equals 90 degrees. Pi halves radians, 90 degrees. I'm not even going to write radians this time. But essentially, we're going to say that pi sixth is actually a 30-degree angle. So one thing I do want to do is this. When you're talking about pi sixth, we are acknowledging that this right here is what we're calling pi, and this is what we're calling 2 pi. What we're doing is we're lining up increments of rotation that are a sixth of the way rotated to pi, or a sixth of pi, or 30 degrees. So I would say that, 30-degree rotations, we'd say 30, 60, 90, 120, 150, 180. You'll notice that there are 1, 2, 3, 4, 5, 6 of these rotations here, and that's because what we're doing is we're saying it takes 6 of these pi 6 things to get over to pi. So this would be pi sixth. We could label these here pi sixth. This is 2 pi sixth. We're going to come back to that one actually. Sixth. This is 3 pi sixth, 4 pi sixth. I'm going to pick this up here in just a minute. We say 5 pi. These are both over sixths. And then 6 pi sixths. Now, before we go to the bottom, one thing I want to say about this is the same thing here as 2 pi, or sorry, just a pi thirds, a third of pi. Thinking that pi is the same as 180, we could say that a third of 180 is 60. And so you could see that these 230s did indeed compose a 60-degree angle here that we're about to call pi thirds. This 3 pi 6 reduces. This 3 and the 6 cross reduce, or just reduce, and we get pi halves. But think about this. Pi halves, that is a half of a way rotation to pi, which is half of 180. This is indeed a 90-degree angle. This 4 pi 6 reduces to 2 pi thirds, which 1 pi third is a 60-degree rotation, so 2 pi thirds would be 2 60-degree rotations. And we could say also 4 pi 6, which is 4 30-degree rotations. And then 5 pi 6, 6 pi 6. But the idea is, if you can memorize 2 pi and pi, then dealing with pi 6, we can say there are 6 of these split ups up here, splits, and then we say down here, we say 1, 2, 3, 4, 5, 6. So we would say that these are 7 pi 6, 8 pi 6, 9 pi 6, 10 pi 6, 11 pi 6, and then this would be 12 pi 6. And of course 12 pi 6 is the same as, you betcha, 2 pi. So we have 12 total pi slices around for pi 6. Let's talk about our pi third. We said a pi third is a third of 180. It's a 60-degree rotation. So you could think of this as, looking this way, we would say if this is pi, and this is 2 pi, then it would take 3 pi thirds, or 3/3 rotation of pi to get over to here. So we say 1, 2, 3. And then down here we also have another 3. We say 4 pi 6, 5 pi 6, 6 pi. Oh, sorry. 4 pi thirds, 5 pi thirds, and 6 pi thirds, which is 2 pi. So we have 6 total pi slices here for pi thirds, and then the last one we tend to pick on is pi fourths. And pi fourths is a fourth of 180, and a fourth of 180 is just a 45-degree angle. Whoops. Let me zoom back out here. I think that I can do this by... I see what I did here. Sorry, thanks for being patient with me, everybody. Okay, let's try this again. But essentially, pi fourths is a 45-degree angle. And we could say that sketching this out, we say that there are 4 pi fourths, not very well drawn, 4 pi fourths to get over to pi. And then to get to 2 pi, we would say that I would need another 4 pi fourths. So there are 8 total pi slices here, 8 pi fourths to get all the way around 2 pi times. But this is what we mean by radian measurement. Essentially, how many times does a radius fit into the arc length that you intercepted with your angle? Because as many times as it fits in, that's how many radians your angle measurement is. Cheers.